Alright, so that's fine. We've got the polygons, they're filled in, but now I'm going to apply per pixel or per vertex color. So the idea is we want to interpolate an attribute, in this case color, between 2 points. Let's say we are interpolating between this point and, why do I always draw these wrong? This point, so along this way, and well, for simplicity, let's just look at red. So this will have, there'll be some sort of red color over here. I'll call this R1, and some red color over here. Well, here, this is a shallow line. The X separation is greater than the Y separation, so the independent variable will be X. We want to track the change in color with regard to the change, whoops, wrong D, in X. So that will be simply red 2 minus red 1 over x2 minus x1. And then what we'll have is, for each point, we'll say the red at the, let's go k plus 1 point, will be the red at the previous point plus dr dx. Because this will be a loop invariant. At every step, x will be increasing by 1. So at every step, the red will be changing by this float. And this will ensure that the red here and the red here it's evenly blended between them. And that's fine. Also, by the way, just for completeness, if we were making a steep line, we wouldn't be dealing with dr dx, we'd have dr dy, because now we would know in our loop that we're stepping y up by 1 in each step. So that's our, our loop invariant. That's y2 minus y1. Okay, fine. But we can do a little better than this, because, well, we don't just want to do one float calculation at a time. We have AVX. And AVX lets us subtract, multiply, add 8 numbers at once. So let me define something called a payload. And that will be a set of a big vector of 8 numbers, where the first 3 are the red, green, and blue, and the other 5 are currently not being used. But that's fine, because it's the same computational costs to add these things together. We're doing them 8 at once. So then what we do is, instead of R1, we'd have, each vector would have a position and a payload, that set of 8 attributes. So then we'd have the change in the payload with respect to x will be, well, the payload at the end point minus the payload at the start point, divide by the x separation. And this, lets us interpolate an arbitrary amount of attributes, which is sort of similar to the way OpenGL works. OpenGL does, to my knowledge, doesn't use it exactly in this way, but the idea is that, what am I thinking? The idea is that in OpenGL, when you write a fragment shader, you're doing per vertex operations, and then the rasterizer intercepts that output and interpolates all attributes. The position is set, GL position, as an internal variable, but the attribute, whatever you pass along to the fragment shader, automatically gets interpolated, and that's pretty similar to what we're going to do here. Right, so let's jump in and get that working. All right, so let's get into this. We'll just go through the usual process. So we'll just open up, oh, no, not that one, not that one. We'll open up control, app, make a function for this. And then just head to the app, and call that OK. And then we'll just grab the code, duplicate it. Okay, so as you can see up above, I'm defining my set of points, my set of positions on the screen, but I'm also going to change the vertex data structure. Wait a second, did I have a vertex data structure? Let me check that. Just go to linear algebra's header and down to the edge table, and actually I don't. So let's create that. So I'm going to need two things. I'm going to need a payload and a vertex. So we'll start with the payload. So think of a payload as just an arbitrary set of data which can be passed through, which has some semantic meaning, but the rasterizer really doesn't care what it is. It's just the way the output gets used. So I'm not sure if I went through this before, but this is a union. These variables are using the same memory space. This lump is all 8 floats together as one variable, so we can add and subtract these things arbitrarily. And this data is an array which accesses into the individual numbers so that we can use them as we need. For instance, data 0, 1, and 2 will be the red, green, blue channels of our shape. So now I'm going to use make the vertex. Actually, I misspoke. We don't need that. I'm just looking at my notes. So we could actually, no, I will make one. Okay. Just thinking on the spot. So this vertex struct is going to be it's essentially going to be the data which is used to draw something. So we'll have the X, Y position on the screen, and we'll also have some attributes. And this will be used by the drawing functions later on. Where was I? So we have we'll have an array of vertices, an array of attributes for each vertex, and there we have it. Okay, so we can go back to our app and start defining this data. And I'm actually going to copy this over because it's not too exciting. All I'm doing is for each of these vertices, I'm assigning them a whole chunk of data where the first 3 numbers are the red, green, and blue channel for that pixel. So, okay, fair enough. We'll keep going down. Okay, so we're setting everything up. We're transforming the points. We're doing the backface culling. And then if we get to this point and we decide that we want to draw, then we'll need to allocate space for the payloads. And of course, right down the bottom, we're going to need to free those payloads. Okay, so what are we doing with this? So we've allocated space for vertices and payloads. Then I want to loop through for each vertex and send that, send that data along. So I'll say, okay. So I'll access into the attributes by the same as before, grabbing the appropriate vertex for the corner of the plane. Okay, so now what I want to do is pass in this edges, but now edges include some payloads, so I'm not going to use a simple clip function. I'll make a general clip function. So I'll just head back to the linear algebras, and where I've got simple, I know there's a lot of back and forth. Okay, so then I'll go to the linear algebras source file, copy this, and the clip function as well. Alrighty. And yeah, it's not the greatest naming convention, but that literally is what it's doing. So I'll just head to the to the header and declare that. Let's get into it. So that seems to be fine. Now at this point here, I'll just head right down the bottom. So the idea now is, we're taking an edge table, and that edge table, where we care about the attributes as well. So I'll just go down and I'll go ahead and free the payloads as well, because we don't need that anymore. And then up at this point here, I'm going to interpolate. So I'll say, okay. Right, so I'll say, okay, let's make a payload. Okay, so for A and B, I'm going to load those in directly from the input, and for C, I'm going to interpolate. There we go, excellent. And we already have the parameter t, which is why I set that function up to return a general float. All we need now is to use it, so we can actually use something pretty similar to this. So I'll say, okay, payload C lump. Okay, so it's going to be t times b minus a plus, okay, that's fine. It just doesn't like the function yet, I think. Oh, okay. Yeah, it needs to be the 256-bit version. There we go. Excellent. So we've got that. Now all we need to do is down below where we add in the points. Let's change this. So and of course we only want to increment the vertex count once, and right at the end after we've added everything that we need to add. Right, so let's just grab this, put it down below. That was B. And down below again. Wait, that was C, wasn't it? Yeah, I'm not losing it. All right. Good. Good. Excellent. So there we have it. That is correctly clipping with interpolation on all attributes. So if you've got a line going from red to green and it gets clipped by the view, then the intersection point, like orange or something, will be visible there It won't do anything crazy. Okay, so with that being done, okay. With that being done, I am going to just change up the order here. So down below where I'm applying this directional lighting, I'll just sort of copy that and apply it over here. So at this point, where we take in the vertices one by one, I want to apply lighting to each vertex. So if I were to be really particular here and map it to OpenGL, this part is sort of working like the vertex shader. It's telling the program, like, where on the screen do we want to draw and what attributes do we want to draw for each vertex. And then later on, I'm sort of making the rasterizer, and then when I come to the actual drawing function where I use those attributes, that is like the fragment shader, if we were to make that analogy. So where was I? We have the torch, and we could define this somewhere else, but I'm just going to put it here. It's not the worst thing. Okay, so what I want to do is I'm actually not going to store this yet. I'll take it, work with it, and then store it in. So what do we want? We want the red, green, and blue. That's fine. So we now load that in, and then I'll load that data back from the diffuse color variable into the attribute. So I'll say attribute and then finally I'll load that into the edge table. Okay, so hopefully you can see we can do all sorts of per pixel operations, sorry, per vertex operations, and then just load them into the edge table and it will handle them. So that's all loaded in. Keep going. Okay, so now I want to change this. I'm going to say draw polygon colored will be the name of the function. And what we'll take is just the edge table, because that includes not just the pixels, but the attributes that we need. Okay, cool. So let's go to the engine and declare that function. All right, so we'll head to the view and engine. And yeah, in the previous video, we drew a flat polygon, traced the edges, and this will be very similar. We'll just need to, let me see. I'll call this blended, and interpolate. I know I'm using slight variations on the same name to mean different things. It's a little weird, but yeah, there we have it. So I'm also going to need a new draw function. So if I go to draw horizontal line, I'm going to draw this 1 pixel at a time, just because I found there was a way to get the AVX2 to work on this horizontal line when the line is blended, but there are rounding errors and things, and it just looks slightly dodgy. So I'll just go with this one here. So again, we need the polygon. Now just double check in my app, draw polygon colored. Now I'll just change that. There we go. Okay. So then for the edges, going to have to change this a little bit. So for the vertices, I'll say, let's have a vertex v1 and v2, and I'm just going to have arrays of vertices. For the reason that I want to track also the beginning attributes. So when we draw a horizontal line, we don't just need to know which x coordinates to draw between, but we need to know, which color to start at. And yeah, so I'll take the same arguments, use them down below. And then for the horizontal, it's pretty similar. I'm just going to use the two vertices, and just for stability, I'm going to specify the y coordinate by hand. Just double checking my notes. Okay, so excellent. Let's take these and head over to the source code and implement them. There we go. Okay, so this will be really just variations on code that we've already written. Okay, so I'll grab the, I know there's a lot of back and forth, so I'll grab the flat polygon code from before and just adapt it a little bit. So before I was declaring these on the stack because an int is quite small, Vertex potentially a little bit larger. So what I'm going to do is I'm going to malloc these basically. Okay, now because we are allocating them, we need to free them as well. Okay, so let's keep going. Oh, whoops. Why did I? Oh, no, I did. It's just confusing me. Okay, cool. So we've got the vertices ready to go. Now, this loop here, we're just setting the y min and max for the screen. That does not have to change, but what we should do is, well, let me see. We'll go vertex start for the y coordinate and set the x to 640. Do the same for the end. Okay. Excellent. Just checking. Okay. Happy with that. All right. So now we look through all of the vertices and we want to interpolate the steep edge. Okay, but then if we look here, we need to set up the two vertices, one for the start, one for the end. So what I'll do is I'll say, alrighty, let's make a vertex, call it v1, and then I'll set the x and the y, and then I'll also set the attributes. Okay, so v1 is set up. Let's go ahead and set up v2. Okay, excellent. So let's go v2x minus v1x, and same thing down below. Okay, so let's go to those interpolate functions. We'll go to shallow edge first, and I'll just pop up the top. Okay, so we'll just rename all of this, so this will be, yeah, just the logical sort of refactoring. Okay, that's fine. And then down here, v1y. But there's something else that we need. We also need, oh, this int pixel, we don't need that. Good spot. But we also need the change in the payload over x, because now x is going to be the variable which increments. So we'll go d 56 d payload dx equals, what is it? Well, it's the quotient, so the quotient of the payload difference over the x difference. So that will be alright, so we have the change in payload with respect to x. That's all good. Now just keep going with the refactoring here, so we'll have v1x. And then we'll be looking at and I'm also going to add, yeah, well, I'm going to make another variable, which is just the start vertex. So what I'll do is, if we want to capture the x coordinate, then we should also capture the attributes there. So vertex start, I'll do the same thing down below. And then, well, as a loop invariant, x will be increasing each step, and because x increases by each step, at each step, the attributes need to be interpolated at each step as well. So what I'll do is I'll say, okay, the fragments attributes, that lump there, is we'll add on, so we'll go 256, add packed scalar. We will take the fragments attributes, and we'll add on to that the change in the payload. Okay, and so what we're doing is we are taking the fragment with all of its attributes, and every step we're interpolating those attributes, increasing a little bit. And then at any point where we capture the x coordinate, we also capture the state of the attributes at that point. And so if I were to just pretend all the other functions are done and just look at the wireframe, then what I would have is I would have a line between each of the corners with the color smoothly blending along that line. And the rest is really just variations on the same theme. It's, you know, making license plates, so to say. So I'll take the rest of this function and copy it. I just realized I can use dx down here. That's nice. Okay. All right, so just double checking. So we're going steep, so we're going to have to increase x based on y. So I'll just flip all of this around. And now we want the change in the payload with respect to y. So it will be the difference in attributes divided by the y difference. We're still going to start at v1, but the temporary variable will now be x. And then the loop variable will be y. Just double checking. All of this is fine. Okay, so again, there we have it. Okay, I'm happy with those functions. We can close those down, pretend that they are working, and we'll find out. So what I want is I want to just draw a horizontal line blended. Is that what I called it? Or did I just, yeah, it should be blended. Okay, cool. So from one vertex to the other at that given y coordinate. Okay, excellent. So I'll now close that down. And then we'll go to drawing the horizontal line. So just go back up to the horizontal line function. Okay, so there we go. So we get the frame. We do not convert the color. We convert it later on. Okay, let's go int x1, and I'll get that by okay, so we're setting this all up, but we are going to need to interpolate again. The first time we were interpolating attributes was on the edge points between the corners, but now we've got our two edge points and we want to interpolate in a horizontal line. So we'll go through the same rigmarole. We'll have a payload, which I'll call fragment, and then the fragments lump will load in basically. Actually, I changed my mind. Let's just do this. And now we'll need again the change in attributes. Okay, cool. Just double checking again. Right. So, I mean, what needs to change? All we need is to get the color for each pixel. So we'll go just the same as we had before, the unsigned character array, convert color. Now for the red, we will need the fragments 0th bit of data. I should say 0th float of data, shouldn't I? So there we have it. So red, green, and blue. But then we need to set this up so that it's interpolating at each point. So we'll just go fragment lump, and we'll increment that. So we'll add the change in payload with respect to x. Fingers crossed. Fingers crossed. Let's see what happens. Okay, okay. Doesn't like it. Alrighty. I must have forgotten to allocate for that. Okay, no worries. So, of course, when we make a new edge table, we need to allocate space. And we are freeing that? Okay, let's see how this goes. There we have it. Yeah, very nice. Okay, so yeah, as you can see, we have a color on each vertex, and along the edges, that is being interpolated, and then also along the horizontal lines between the edges, it's being interpolated again. And this same practice will work for any arbitrary data. We can send up to 8 floats in one go and it will interpolate them just the same way as it's interpolating these colors. And if we need more than 8 floats, we can just set that by hand in the struct and what? One operation becomes 2 operations. But anyway, the point is we've got it working. It looks very cool. Frame rate isn't the best, but that's fine. Okay, so yeah, by the way, just to tie this all together, remember before I was talking about the vertex shader being, where are we? Sort of this part here where we were doing any per vertex operation on the attributes before we pass them in to be worked on. The fragment shader is sort of being played by this draw function here. Okay, so the rasterizer are these functions here. They are interpolating the attributes between the vertices, and the fragment shader is sort of this bit here. So it's reading the data, we can alter data and things. But anyway, so yeah, so that'll be it. I hope you had fun, and I will see you again soon in the next video where we apply texture to these faces. All right, bye.